Thank you. Thank you. Good morning, everyone. I hope you can. Am I readability 5 at the back? Okay, thank you very much.
You have a funny accent.
I'll do the same this afternoon, Don. Yeah. Anyway, thank you for coming along. This is an expanded talk. I gave a talk in April at the GMDX convention, which I thoroughly recommend everyone to go to, just about 15 minutes. And Martin G3ZAY collared me at the end and said, would you like to give an expanded version of this at the convention? So that's why we're here today. I've got roughly about 50 PowerPoint slides. I'm only going to talk for about half an hour, excuse me, and then please feel free to interrupt at any time during the talk if you disagree with anything that I say, etc. First of all, I'm not suggesting that you go home and take the lid off your brand new Gemini and change R31 from 1.8K to 1.2K. The whole point of this is just to draw your attention to the fact that a lot of commercial equipment takes an awful long time to do things. And that's the key point. You can make your operation a lot snappier, whether it's on SSB, CW, or data modes. So it's just some recommendations today, some suggestions to get you thinking about, does it really matter how long it takes to go from receive to transmit, and then from transmit back to receive. So here we go. Some of the advantages. If you've got an amplifier, now some of the slides have got quite a lot of texts. I'll try and leave them on the screen as long as possible, and I know I find it difficult to read and listen at the same time. So here's the first thing. The first advantage is if you have an amplifier, your transceiver hot switching is really not an issue. So if you're only running 100 watts or 200 watts from a transceiver, you're unlikely to damage anything. As soon as you connect an amplifier, there's a lot of things that you need to consider. First one, the transceiver delivers RF too quickly. And that's why most transceivers, I'm just using this is point number 1, have a TX delay built in. Normally the default's about 8 milliseconds or 10 milliseconds. In other words, after you press the PTT, whatever method you're using, there's a delay of a few milliseconds and then the RF appears. That's a standard setup for every transceiver. When I was younger, I wanted to have a bit of power in my station. I was building homemade amplifiers. I had no money to buy vacuum relays, so I used open frame relays. And of course, they take a great long time to transfer and to close. I brought along a few props. I'll pass them around if you like in a little while, a few bits and pieces for you to have a look at. But as I said, please feel free to interrupt with any questions that you might have. The last one, forgetting to connect the PTT cable, we've all done that. And it's easy to do. So that's the first advantage of having short switching times. Or should I say more accurately, sequenced switching times. In other words, not just short, but you've thought about the exact sequence of events. The amplifier output relay has to go over first, then the input relay, and then the transceiver has to deliver the RF, and everything should be okay. This is perhaps a more significant thing, that if you're on transmit and receive, the first one, we've all worked HB4 AGN and said that can't possibly be HB4, it must be 5 Bravo 4. A surprising number of stations have this problem. Last night I was hearing about Papa Alphas coming out as a Golf Alpha, and they don't know that they're not sending the first dot. So on CW transmit, that's the second one down, you've got to, let's make sure that you send the whole part of the character. So if your call sign starts with a dot, you've got to pay special attention to making sure that that dot is sent by whatever method of changeover you're using. I'm afraid I fit into number 3. At age 67 years, I'm still terribly impatient. It can be very irritating if you go back to receive and you've missed a bit of a calling station. Some of the pile-up stations we work on, our expeditions, are very, very speedy, and they're sending before you get back to receive. On VHF, of course, I've just mentioned it in the passing there at the bottom. I've got a little sequencer that I made. and it does exactly that. It switches on the masthead preamp, switches off the masthead preamp first, then it powers up the amplifier, and then it powers up the transceiver. So the masthead preamp cannot be transmitted into, which is very crucial. Okay, so that's the first, the three real advantages of speedy times, and number two is the most important one. You're saving a few milliseconds in every single QSO, and if you take that over a 24-hour contest or a 48-hour contest, it really does make a difference. There's my little test setup, a very untidy corner of my little shack. I borrowed this digital storage scope, an Agilent, it's not a latest model. I couldn't figure out how to export the screenshots, so I'm rather embarrassed. I had to just take a picture. You'll see them there. So here you can see I'm testing a friend's micro ham with an old TS-870, one of the first DSP radios, or completely DSP. That's a little Agilent just with the probe stuck on the thing to make sure that the frequency response is correct. Very useful device for these sort of tests. Right, let's move on. Some history. 100 years ago, they would probably be using one of these, the famous knife switch. And on field day one year, about 10 years ago, we actually used one of these because they're dead handy for changing over open wire line. A bit slow. Anyone like to guess how long it takes to go from receive to transmit with a knife switch?
Seconds. 800 milliseconds.
What did you say, Robin?
800 milliseconds.
Well, here's the scope. This is the closing of the top trace is the closing, and the bottom trace is the signal arriving at the other side. 200 milliseconds per centimeter on the time base, so 400 milliseconds for a minimum changeover 100 years ago. Okay. Some other changeover devices. This is a 1940s US military Ntype coax relay. Of course, Ntype should not be called Ntype. It should be called Union Guide 22/Universal. And it's named after a guy called Paul Neal. That's where the N comes from. And as you know, the pin and everything is the same size as a BNC, the male connector. I've got a wee video of this changing over, and while I'm playing that, I'd like you to think what the timing might be. This is just a little video, just 5 seconds, I think. There we go. So I'm applying about 70 volts DC. So this is from I think it was a US Air Force changeover device. Right, any estimates how long that's taking to go from one side to the other? 100? It's surprisingly quick. There's the traces, 20 milliseconds per centimeter on the x-axis, so about 25 milliseconds. It's actually pretty quick for something that's 1940s. I think it was US Air Force. It was in a VHF sort of 832B, 829B transmitter.
Is there a bit of bounce on that?
Probably there is on the, I think this is probably bounce here.
Oh, okay.
Yeah, but coming back to bounce in a minute, Bob. Okay. So that's two very ancient devices. Moving forward a bit, we moved into the era of trying to do things even faster. And in this era, the transmitter was permanently connected to the antenna. Sorry, I keep forgetting this. So here we have a situation where the transmitter is connected all the time to the antenna. And as soon as you press the key, or whatever method, pressing the key, it biases the valve. And, when you're on receive, the signal goes through the valve, if you like, to the receiver port. When you press the key, the first few cycles open that route. Now, this can be done in, David's an expert in this, G3YYD. This can be done with solid-state devices, but there are problems. Some wonderful names on the parts list. Sarks-Tarzian. It is the selenium rectifier made by the Sarks-Tarzian company in 1961. Moving forward a little bit, so that was a TR switch that would be extremely speedy. They do warn that they cause TVI, but of course that was in the days of Channel 1 when we had 45 megs plaguing us, secondary harmonic of 28. This is a thing that came up in November 1986 from Peter Hart, how to speed up a relay closing. So what he's done is connect a zener in reverse, or it depends which way around you think the zener should be, in series with the diode which is used to suppress the EMF, the back EMF. So as you know, when a relay is disconnected, the magnetic field energy has to go somewhere. So the magnetic field collapses and it can generate several thousand volts. So you put a diode across it to protect the circuitry there. If you put a zener in that configuration, it actually limits the amount of the back EMF and speeds the whole process up considerably. So I thought, I'll try this. It's going back 30 years, but just because it's an old idea, it's not necessarily a bad idea. So here we go. This was my friend David, Dave GM4 EVS. He's a bit better at getting stuff out from his scope. The yellow trace, the top trace, is the test pulse. This is just one of these little Omron PCB plug-in relays you might find as the input relay to, say, an alpha amplifier or a ACOM amplifier. So this one might be the input relay of an ACOM style amplifier. So closure time 2.5 milliseconds, 3 milliseconds because of the diode. So the ordinary diode across the relay is slowing the whole thing down because the data sheet says 1.2 milliseconds. If we put a diode across it, that's the configuration that Dave used in his testing setup. So the 1N418 is there, the standard thing that you find in all amplifiers pretty much. He put that there, 12 volt zener. Here are the new traces, and now the release time is way down to 1.37 milliseconds. There's a disadvantage. It makes a very loud noise as it closes. It's like a rifle shot, he says, bang, and it might give you a fright, you might jump. So there are ways of speeding up the release time just with a little bit of circuitry. Yes, David?
There's a cheaper way, and that's to use a resistor instead of the zener.
Yes.
And I won't go into the detail, but basically you just ratio it between the resistance of the relay and the maximum voltage the transistor will take.
Okay.
Because then what happens is effectively it works as a voltage divider.
Yeah. David.
And, you have to do the calculations.
Yeah. David G3YYD saying there's a cheaper way to do it with a resistor instead of a zener. But I don't think a zener is very expensive, David.
No.
Okay. I was the 12 volt, yeah. If we go back to, it's a 12 volt, so roughly equal to the power rail voltage. I don't think it matters too much as long as it's not too low a voltage. Okay, so that's one trick for speeding up a relay releasing, going back to receive or whatever setup. Let's talk about some devices that are available nowadays. Almost every high-power amplifier like the Econ 2000A has a vacuum relay in the output. The reason that they're used is they're very compact in size. Because there's a vacuum inside, they can handle a tremendous more power, but not if it's trying to be switched. Even a vacuum relay can be flashed over if you try to switch it. This is a Jennings G1E. The spec sheet says 8 milliseconds to open and 8 milliseconds to close. So I thought I'll test this with my rather rudimentary testing system, and I found it closed much more quickly and it opened much more quickly. When I added a zener across it, it was very fast indeed, and it wasn't too loud a noise. Again, that would be probably a good thing to do in almost every shack. Make sure that the output relay of your amplifier changes over very quickly. So you can adjust them. There's also a method for making relays close more quickly, but I'm not going to talk about that today, but it is an accepted method. Bob mentioned bounce. Here's a classic example. This is the vacuum relay. Not only have you got the relay to either open or close, but you've got to let it have time to stop bouncing. And you can see the bounces there on the top trace. as it settles down. And of course that's adding 2 milliseconds on the X time base, so it's taking another 3 milliseconds or so to actually settle. And again, it's very important that you let the relay settle down. Okay, some other devices, the early flex radios use small versions of these read relays called the Crydom read relay. They're very, very fast, well, about 3 milliseconds, I think, the spec. They can handle a lot of power, can handle about 1800 watts, and they're not that expensive. It's, I've got all the stuffs at the front if you want to come at the end and have a look. At the GMDX, I passed it round the room, and I'm not sure that I got everything back. Paul was the first suspect. So that's another switching method that was used quite a lot in the early flex radios, these high-speed read relays. A bit more costly, about $100 each. The Alpha 87A is an old amplifier now. It's been around for about 25 years. It used these pin diodes. It's fairly straightforward. You forward bias it and it carries RF. You reverse bias it and it doesn't carry RF. And the trouble with them is any hint of hot switching and they just blow, and it's an expensive, difficult repair. Even the latest Econ amps, I think, have avoided that problem by using these vacuum relays. They're steering clear of this very speedy technology, but a bit fragile even in 2018. The current flex radios and the ANAN, etc., are full of these little devices. They're RF switches. They're very fast, 1.5 microseconds closure, 1.5 microseconds opening. They have a big disadvantage. What's the disadvantage of them? Any? Pardon? Power handling, yes, and also the main one is isolation. They've only got 30 dB of isolation. And of course, if you have a powerful amplifier, you cannot use something like that. But you can put 2 or 3 in series because it's HF, but that again introduces loss. So it's a bit of a balance up. These are used in all the current SDR transceivers that are on the market in various roles throughout the machine. A semiconductor RF switch, SMD. Right, some methods of switching over. Hand switch or foot switch. This is a Shure 201 mic, which some of us older people here might remember, specially designed to keep the over short. The spring's so strong, you have to like this. Yes. So, creaky, yes, as well. You know which they're using, but excellent mic, the Shure 201. So that's hand control. Foot switches, we settled on this type of foot switch. They're made in made in Austria, and these are really excellent. I've got it here in the front for you to look at later. They've got 3 micro switches, and you can hit either one. We used to have the DVK on the middle one, and either the left or the right would put you on transmit. So if you're on a de-expedition, and this is full of sand on the ground, and your feet are full of sand, and this thing's moving about, these work really well. I've taken the weight out of this one. When you get them, they've got a heavy weight, about half a kg of melted steel.
They were originally used, I believe, on sewing machines.
Yes, this one I think was a dictaphone one, Robin. Okay. So either sewing machine or a dictaphone. So foot switch, I'll come back to foot switches in a minute. Software control, we've all got this, I think, either via the CAT control or a separate PTT cable or via the interface. Moving on, this is a method I use at home, parallel processing if you like, instead of serial processing. If you press the mic, the transceiver has to go to transmit, and then it has to put the amplifier on to transmit. If you switch them both together, it's much faster. Similarly, going to transmit and going back to receive. There are a few problems. Some modern radios don't like the 0.7 of a volt voltage drop across a diode, so you have to connect them straight to the foot switch or whatever. But this is the system I use, and it's very fast, and it doesn't involve much engineering, just a little box with some diodes and some phono sockets. You plug your PC interface into one, your foot switch or whatever into the other, and it's really fast operating. So parallel switching instead of serial switching, if you like. Very speedy, but you do have to watch because some radios will not actually go to transmit. Okay, Those that have just arrived, we're looking at transmit, receive, the different methods. And we've got to Footswitches, and there's a enlarged photo of that made in Austria Footswitch that we use with the 3 micro switches. They're really, really good. I thoroughly like them. I don't like any of the commercial Footswitches. I haven't tried the DX engineering one, Tim. I don't, the one beginning with H and 4 letters is horrible. It's got too strong a spring, too small, it's just awful product. Moving on, some things you should really avoid, and this is a little bit controversial. I'm trying to avoid controversy today. A lot of people like QSK. It's horrible, absolutely horrible on a de-expedition or in a contest. Why on earth would you want to listen between your transmission, which is only 2.5 seconds long? Yet the amplifier manufacturers and the transceiver manufacturers put an awful lot of effort into enabling you to do this. I just hate it and would never ever use QSK. It's tiring. You're trying to listen to stuff that's irrelevant. I'm talking about a contest or a de-expedition here, and you're probably not sending fast enough if you're using QSK. Okay for rag chewing by all means, but not for anything serious. It's tiring and just noise, not a good idea. Stressing the amplifiers, stressing everything. Similarly with Vox, is Tom here in the audience? Tom is famous, we're multi-multis, we don't need a DVK, you just press the mic button and Tom calls CQ for you from the other side of the room. So you just sorry, Tom. So in a multi-operator environment, Vox is no use at all. We used to call it aux, and it's completely unsuitable where there's someone else in the room with you. So please try and avoid these 2 things. There's a third thing I don't like as well, but I won't mention it. It's called ESM. I hope there's no fans of ESM here. Okay, I'm watching my time. We've got about 10 minutes more. Peripheral devices. Most modern radios, I'll say a K3, ICOM 7610, etc., have a built-in interface. The SDR transceivers, of course, the interface, the computer itself and the radio are integrated into one box. So that's when. The problems start when you need to do things externally. So this is a setup we use on our de-expeditions. It's a little ICOM 7300, which performs really, really well. Everything is done through one cable apart from the audio. The 7300's got a built-in DVK, which works really well also. You just make a little ladder box with 4 resistors and you can have 4 pre-programmed messages on SSB. At the back, you might be interested, I added a receive antenna input to the little 7300. It's a very lightweight radio, that's why we take it on an expedition. But this little box, I guess you could call it a front-end protector and a receive switching. The commercial cost of this is vast, but I looked at the thing and I said, this is just 2 phono sockets and a TMP plug and a TMP socket. And I thought, I'm going to make one. So we just made a little panel, a sort of sandwich at the back. Luckily, there's an unused, sorry, I'm pointing. There's an unused space at the back of the ICOM 7300 where this little metal panel fits. And this box allows you to, when you're on receive, you can either select the receive antenna or the transmit antenna to listen. On a de-expedition, there's probably another station just 25 meters away transmitting a bit of power on another band. So this also has a relay in it to short out the receive antenna when you're on transmit. Start the one on each station, and that covers that. Okay, sorry to be rushing on here. Here's where things start to unravel a wee bit when you add in an extra layer of software and an extra device called a router. And I'm afraid one of my least favorite devices, the name begins with an M and the end in ham. I first used a micro ham at ZM4A in 2004, and I pressed the F1 key to send CQ, and nothing happened. So I'm looking at the guys, what's wrong, what's wrong? And it turns out they were using a pretty slow PC. It was still, for its day, pretty fast, but it probably didn't have sufficient RAM. What you're doing here is these interfaces that are now probably not going to be so needed have an extra layer of router software. So you've got WinTest or something down here, your logging software. You've then got the router software involved, then the microham or whatever, and so there's a thing coming between the computer and the transceiver. And anything between the computer and the transceiver, especially if it's software, is a bad idea, slowing things down. There's a microham, that's the back of the microkeyer 2A. You can see it's a very complicated device. I would not like to be the person wiring up them DB39 plugs. Can you imagine that? What a tricky job. You make one mistake. Very complicated. There's the block diagram of the microham. Yes, it does just about everything you want for controlling your station, and it's got a sound card and all that stuff. Very complicated piece of gear. It's got paddle input at the bottom and a foot switch. I had to play with the settings. Unfortunately, you can set all these to 0, but you can't set the tail to 0. And the implication of that is your PC knows what message it's sending on CW. It knows to send CQ K3LR, just these two words. But it doesn't, the interface doesn't know when the message ends. So after the PC stops sending, the interface waits a certain time before you can send anything with the paddle. Now, a top CW operator would hardly ever use the paddle, but there's always a time when you want to say hi Joe or hello Fred, or you want to paddle something after a pre-programmed message. And that tail delay is a real nuisance. I'll just let you read this slide for a moment. We can set the start delay to 0, but the minimum delay is 10 milliseconds. This causes it to unkey. So this is very annoying because the microham is controlling the PTT line, but the PC is already saying, let's stop sending. So if you put these little carrots in the message, I'm sure it should be carré. If you put the little carrot in the message, it stops the microham tripping the PTT line halfway through. This is a rather specialized case. It might not apply to everyone's use of the microham, but again, it's trying to squeeze the last millisecond out of the process of changing from receive to transmit. I've got a couple of short videos with sound. I don't know how the sound will come over, especially since it's not plugged in. Not to worry. If you just watch the PTT light up here at the top on the microham, this is a Kenwood TS870 just with the PTT light. So this is the message with no carrots, carrot free. So it's just sending my call sign twice. Maybe 3 times. Okay, so you can see that if you had an amplifier and a radio all connected to that PTT line, they're all going to go clunk, 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 clunk during the transmission. Right, here it is with, I just put 3 carrots in. This is the next one, says he, trying to find it. Oh, sorry, went too far. This is supposed to be another video. Here we go. This is the last video. So this is with 3 carrots. It's a wee bit short of the gap. So a shorter gap with only 3 carrots, but it gets rid of any possibility of that annoying relay cycling during the transmission. Right, moving on. If you're just a single op, this is an excellent little device from Lsaid 5VK. It's very cheap compared to microham. It does everything apart from the audio processing that the microham does. The only catch is you have to make up a little CAT cable with a 3.5 millimeter plug, and it goes in there then to your RS232. So I thoroughly recommend this wee thing. Excellent if you're an expeditioner. It combines into one little box lots of functionality that we used to have on separate boxes. It's called the Simple USB Control and Something Interface by Lsaid 5VK. It's powered from the USB, and it's very ideal for a de-expedition CW or SSB. Okay? I've got one of these at the front here. Everything's for you to look at. Right, SDR is the buzzword of 2018. Everybody wants a Flex 66M or something like that. So I thought, well, hang on, let's just see how they perform. I'm afraid so. There's no such thing as a free lunch, as they say, and the all that processing power slows the whole transmit-receive sequence down. Disappointing. I think they will crack the problems eventually. Maybe there'll be a new layer of processing power, but DSP stands for delay. There are two key problems. Latency. Now that's the time it takes from the RF signal arriving at the antenna socket to the audio leaving, corresponding signal leaving the loudspeaker. Turnaround time. If you've got an SDR, it's sure to have a load of digital processing in it. There'll be registers to load, buffers to clear, all that stuff. It all takes time. And you might say, well, it shouldn't take that long, but it does. I'll just deal primarily with the latency. Most of the latency is determined by the filter type. If you're happy to have a poor shape factor, the SDR is reasonably low latency. If you want this narrower frequencies, this higher shape factor, better shape factor, it takes longer. And interestingly, the little Econ 7300 that I mentioned a while ago, it's actually very good. It's got quite low numbers, as we'll see in a minute. So the Flex 66M is nearly a fifth of a second. You could almost read a newspaper while the signal's traveling through the Flex 66M. Very slow. These graphs are very kindly from Rob Sherwood, NC0B at Sherwood Engineering. Rob hasn't put these online yet, but he very kindly helped me by sending me these graphs. What do they mean? Well, the left-hand marker is the pulse going into the receive antenna, a 10 nanosecond rising pulse, designed to simulate like electrical fence interference. The second time marker there is the audio appearing at the loudspeaker. I asked Rob what criteria did he use for deciding when it had reached peak audio. He just said the first peak, basically. So look, this is a 756 Pro 3, been around for about 12 or 13 years, got quite a lot of DSP in it. 2 milliseconds with the wide bandwidth, 3 kilohertz. Narrow the bandwidth down, 6 milliseconds. So same radio, same input pulse, 3 times longer for it to travel through the DSP filtering. That's this. Right, so that's an early DSP radio, the Pro 3. Moving on, here's the little 7300 wide bandwidth, SSB bandwidth, 3.66 milliseconds. We're looking up in the top right-hand corner, and go to narrower, about 7 milliseconds. So still pretty fast, pretty low time for the signal to travel through the receiver. I didn't get time to test any of my vintage gear like the KW2000. Yes?
Years ago, I tested an R4C on sideband.
Yes?
And it took 1.2 milliseconds from antenna to the...
For the passing through. You may not be able to hear David. He's saying that his R4C years ago took 1.2 milliseconds for this latency, the signal arriving at the antenna to reach the... On SSB.
I can't remember the 500.
Yeah. So very good low numbers for old analog radio. Here's the Fluster of the Flex. Look at that, 170 milliseconds. That's its set. The Flex default is medium latency. That's the medium latency, which sort of middle quality of shape factor, if you like. Still 105, a tenth of a second, and 58 milliseconds. Now, quite honestly, in a pile-up, you might not think that a fifth of a second matters, but it certainly does on these really heavy pile-ups on contest stations or on the expeditions. Every fraction of every fraction of a second counts. So just the last few slides, the 6600M. I put this in a table. Really all it tells us is that SDR transceivers are much slower than older radios in terms of the time taken for the signal to pass through them. Nothing really to worry about there. These are all the turnaround times that I mentioned, the second factor. So some quite high numbers there. Just moving on. QST have taken this on board. in their reviews, they now look at both timings when they're testing a radio, not just the turnaround time, but the time, the latency. Here's an example. April this year, they tested the 8000 DLE, and they came up with these numbers. This is the thing that they've, for several years, I think 2 or 3 years, they've been looking at latency. They've now added in the time it takes to change from receive to transmit. So the possible maximum time, depending on your settings, is about 1/3 of a second. Quite a significant amount of time for one of the more modern SDRs. Just finishing up, here's an urban myth. A Windows PC cannot send good CW. And the makers of the Win key and all that stuff, they've made a great deal of this. It's wrong. Win key can send perfect CW, but not if you're asking its old CPU with hardly any RAM to run background apps, skimmer, LP pan, connect to the cluster, power a micro ham. All these peripheral things are what causes a problem with a basic PC. So when we go on expeditions, we just take old XP laptops. They cost £60 each from eBay, and they run WinTest with little interfaces like this, and we've no problems at all with timing or how quickly we get back on receive for the pilot. Summary. These times do matter. I know they're only milliseconds, but it's a cumulative effect. Taking over a 48-hour contest, you can make a lot of extra QSOs in the time. You should try and minimize them, irrespective of your style of operating. Milliseconds do matter. I should have got a badge made. And have a try. Please go home, think about this, experiment, but always check with a local that you are sending the whole of your call sign and that you're not hot switching anything in your station. I'd just like to thank a couple of people for their help. Rob at Sherwood Engineering, ARRL Labs, they were very happy to share their information with me. Dave, who'd done some tests on this before I talked back in April, and Doug, who gave me the information about the carrots. Any questions?
Just make a comment about the 7300. The reason that's got such very low latency, it's the filter type that it uses, the software filter type. Also, it doesn't have the issues of latency inherent in having a network connected to the radio, like Flex or Anan. And it doesn't have the issues of latency in the audio on the computer. But the Flex the 7300 is using something called an IIR, input impulse response filter. So it's not such a fantastic sharp filter, but you get this very, very low latency. And that type of in a single box design is the only way you'll get an SDR with low latency.
Thank you, that's a very good point. Did everyone hear that? About IIR filtering. In other words, the 7300 is using a particular type of filtering which allows it to do not such good quality as some of the Flex radios. Thank you very much for listening, everyone. Any more questions? Roger?
Why don't you like ESM?
Pardon? Why don't I like ESM? It's horrible. There's always ESM, enter sends message. In other words, on CW, you just sit there you type in the call sign, you hit the return key. For starters, I've always encountered with WinTest, WriteLog, N1MM Plus, there's always a set of circumstances where ESM loses the plot. Something goes wrong, or you go back to the wrong station. There's always something that maybe works for 10 QSOs, and then you get very flustered when you've got a raging pile-up if you have to do 6 backspaces. I just don't like it, Roger. You don't use it, do you? You don't use QSK, by the way, do you? Anyway, I'm sorry, we're a bit short of time. A couple more questions. Jeff?
Yeah, one thing that we haven't mentioned there was AGC recovery time.
Yes, I think that's included in the turnaround times. So in other words, when you go back from transmit to receive, you've got to let the whole receiver come back to life. Yeah, I think that these timings would be included in their turnaround time measurements.
Oh, you mentioned pin diode switching the G1E HF1K amplifiers using pin diodes.
Yes.
And, that's working very nicely at well over 1 kilowatt hour per ton cubic DSK.
Right, thank you. So Gemini's got pin diodes at work.
Okay, thank you very much, Chris. We've heard in Kim's presentation earlier that size does matter, and we've heard in Chris's presentation